Okay, so I'm gonna go over our quiz 2 briefly. You guys took that yesterday. What do you guys think? How was the quiz? Easy, bad, okay. Straightforward. All right, so not bad. Okay, so we have thoughts from here and there. Um, yeah, so Kevin, 50 over 50, that sounds good. So I put 3 questions, and I thought the last question, or maybe for some of you, it might be the last question. But so this is the quiz 2 that you took last night. First one, setting it up, so that shouldn't take you more than 5 minutes. That's what I would say. Number 2, yeah, you kind of have to do some work to get to the answer, but you don't again have to solve it completely. So that also doesn't require too much of your time. The one that requires some of your time will be number 3, which I have listed here, but it could be number 1 for you. So that was the only solving problem I gave for this quiz. And everything else was just kind of checking and setting things up. So I saw the scores. You guys did great. So good job. Some of you are getting there. That's still okay, right? So by the time exam 1 comes, hopefully you guys are ready and do well on the test. Okay, so any questions before we start? So let's go over the quiz before we start our session for today. So Sadia, I'm gonna mention what's on exam 1 tomorrow, more detail, but as of now, it's gonna be everything from chapter 2 as far as we go for chapter 3. So tomorrow we'll decide where to draw the line for chapter 3. But you should be preparing yourself with chapter 2 materials. Chapter 1, which we briefly covered, a slow field and a classification. So that was the only thing we did from chapter 1, and mostly chapter 2, of course. Chapter 3 will draw the line tomorrow, so that way you'll know exactly which sections are going to be on our first test. Okay? All right, so before I start, one more thing I want to mention, because I know I'm going to forget. So I'm going to send all of you an email through CUNY first later tonight. So if you don't get an email from me by midnight, 12 a.m., right? Send me an email tomorrow. So this is just a way for me to test that I have your right email address, because that's going to be the email I will be inputting in Dropbox so that you can submit your scrap work or your written work for exam 1 through Blackboard link that I'll be sending out next week. But tonight I'm just going to be sending you a test email just to make sure I have the right email address from you. Okay, so just look out for an email, and if you don't get an email by midnight, send me an email tomorrow whenever you wake up or whenever you're on your phone or your device. Send me an email, say, hey, I didn't get an email, so I can add you on the list. Or just make sure you have the right email address on CUNY first. That way you don't have to double check. So I'll probably send it out around 11 p.m. or 12 a.m. So yeah, I will take a break after class and then write a test email for you guys. So okay, so that's the only update I have. So Leonie, you asked how many questions on the test. I don't know yet. uh, I'll go with 10 for now, but we'll see. But most likely it's gonna be 10 to 12 questions. So I'll give you more details tomorrow as I progress through and think about how much time I'm gonna give you guys, how many questions, and so on. Okay, so tomorrow we'll have more info for the test. All right, so okay, having said that, let's start with our quiz 2 solutions or answers. So again, if you want to speak through your audio, please do that. So for the first problem, so here you have an application to tank problem. So So, all right, so you guys answer each other, so that's good. It's on the syllabus. Everything is, all the dates are on the syllabus, so if you want to make sure it's up there. And the easier way to remember is there's always something every Tuesday, so that's how I kind of scheduled it when I was preparing for the class. So, right? One way to check on yourself. All right, so let's start with briefly go over these questions so we don't miss a lot of time. For this question, the tank problem, we want to set it up so you already seen the question, you already answered the question, so you know that you're going to be using the formula. So let me write down the formula first. So we're going to use dq dt is equal to rate in concentration in minus rate out concentration out. Concentration out, we're going to measure it using the formula Q of T over V initial plus the slope, which is Rn minus R out times T. Okay, so that's the formula you're going to be using along with the initial conditions. Q of 0 is what? Okay, so a 10-gallon tank is filled to the top with pure water. So that should give you a hint for the initial condition. What does it mean to be filled with pure water? Right, initially there is no salt. So thank you. So we know this is going to be 0. Okay? So we have 0, 0. Q 0, 0. Now let's set up the differential equation. So we have dq dt. So water, which has 20 mg of salt per gallon, pours into the tank at a rate of, okay, it's cut off, but I think it's 1. So this got cut off. I believe it's 1, right? Yeah, it's okay. Thank you, Liana. Looks like it was 1. So we have rate in, concentration in, minus, and it is well mixed, flows out at the rate of 2 gallons per minute. So that's 2 times Q of T. Now you have to find the equation for the volume. So we have V initial. What's V initial? Right, so plus, and then rate in minus rate out, that's going to be negative, because 1 minus 2, that's negative 1 times T, with the initial condition Q of 0 is 0. So that's the setup. So it looks like this was the choice. And then if you have to solve it, well, this is a linear first order, so you will find, well, first you would move the term involving Q of T to the left side, and then look for integrating factor mu, and then you will be solving it from that method. Okay, so that was the first problem. Well, one of the problem, right? It couldn't be the first problem for everyone. All right, so the second one, you just have to test that when you take partial of m respect to y is equal to partial of n respect to x, right? So that's what you're testing. And then if it's true, then that's exact. If it's not, then it's not an exact equation. So you just run down the list. The first option we have, is that exact? Dris, do you have a question? Yeah, I am. I'm using a different device. Yeah. All right. Thank you for checking on me, because yes, I do often forget. So thank you. So for the first option, is that exact? What is it? Do you know? So did anyone check what type of equation was the first option? So Kevin says linear. Let's see. No, it's not linear because you have sine of y. It's separable, right? You have e to the x cosine y, x sine of y. If you try to move them around, you can actually write this as a separable equation. So this one is separable. Well, we don't need that for this question, but it's good to know, right? So for the test, if you have to identify, you can always check. What about the second option? Is it exact? Okay. What about the third one? Okay. Fourth? All right. What about the fifth? All right. So this one is linear. Okay. So the correct choice will be whatever choice you had. I think I put like 8 choices, but that's just to give you more options. So, okay. So the correct choice will be 1, 2, and 3. Those are no. Sorry. 2, 3, and 4. Those are the exact equations. All right. So and number 3, you have to solve. So which method did you use to solve this equation? Right, so this was an exact equation, but you have to rewrite this term right here. So we write it as dy dx and then multiply it by dx. So you have 3x squared minus 8x cubed y plus 2 times dx plus 3y squared minus 2x to the fourth plus 2 dy equals to 0. Okay, so this is our function m, and this is the function n. And yeah, you can fill in the rest. So I'm not going to show work. I think you guys kind of figure it out, right? If not, then I can definitely show work office hours. So if you want to come by, see how it is done, I believe the correct answer was this one. Yeah, so yeah, so that's our second quiz. So I hope you guys had fun. I think it was a fun quiz. So I'm looking forward for the next what's coming up. That's our exam. All right. So moving on to our lecture for today. So here's what we did yesterday. We talked. So I cropped these theorems from our textbook. That's why they're blue. So they're written from the textbook. So first we started talking about theorem 3.2.1. So this is still continuing section 3.2. So this is still section 3.2. So we're going to prove some of the theorems, and then we're going to learn what is a Wronskian, and then move on to 3.3. So first we talked about the existence and uniqueness theorem. For this theorem, you don't need to know the proof. So no need to prove this one. So you can know the statement, know what it's saying, know the importance of this theorem, but the proof is, we're going to ignore the proof for this course. Okay. Second theorem that I stated yesterday was the superposition principle, which stated that if you have two solutions, y1 and y2, for the given differential equation, homogeneous, then their linear combination, meaning if you multiply those solutions with constants c1 and c2, arbitrary constants, and write them as a sum, then that is also a solution to the given differential equation. We're going to prove this, and for this one you have to know the proof. So I will show you how the proof works, and the book also does a good job proving this statement, but up to you which proof you prefer, but of course they're similar. So every time you're proving a mathematical statement, you always assume the if statement, okay? So in this statement 3.2.2, if y1 and y2 are two solutions to the differential equation 2, well, the differential equation is right here given to us. So we're going to assume that statement. So here's how the proof goes. So again, let me know if you guys have any questions on any of the notation, because it's important that you understand the notation before we start doing computation. So it's very important that you do that. So assume that y1 and y2 are two solutions to the differential equation which is given to us, L of y equals y double prime plus p of t y prime plus q of t y equals to 0. So we're assuming that these two are all solutions to that. Well, what does it mean? That means when you plug in y1, you also get 0, and when you plug in y2, you also get 0. So that means L of y1, we can also write it in the same form as equation 2. So we'll have y1 double prime plus some function p of t y1 prime plus q of t times y1 equals to 0. That's what it means to be a solution. And y2 is also a solution, so we can also write L of y2 is equal to y2 double prime plus p of t times y2 prime plus q of t times y2 equals to 0. So that's what it means by the assumption we're making that y1 and y2 are solutions. Well, what do we want to show? We want to show the then statement, which is that their linear combination is also a solution. So we want to show that this expression, so c1 times y1 plus c2 times y2 also solves the differential equation. So that's our claim. We want to show that. Well, let's show. So if I plug this into L of y, what do I have? So if I do that, I have L of c1 y1 plus c2 y2, right? Well, what is L going to do? Well, it's going to plug this into y and take its second derivative, so we'll have this expression c1 y1 plus c2 y2, take its second derivative, plus then it's gonna multiply with this function p of t c1 y1 plus c2 y2 and take its first derivative, plus, and then it's going to multiply with q of t times c1 y1 plus c2 y2. Okay, so that's what L is going to do. Now let's simplify this. Well, because differentiation is linear, I can go ahead and differentiate each term by term. So for the first bracket, I can differentiate y1 and y2 second derivative, so I can differentiate it twice. So you will have an expression that will look like this: c1 y1 double prime plus c2 y2 double prime plus, and I can do the same thing with the second expression, differentiate it one time. So you'll have p of t times c1 y1 prime plus p of t times C2 y2 prime. And the last expression, I'm just going to distribute Q of t. So that would give me plus Q of t times C1 y1 plus Q of t times C2 y2. Okay, well now we're going to rearrange them in a very clever way. Okay, so I'm going to go ahead and collect terms involving C1 and C2. So let's pull out C1. So we have y1 double prime, and then we have p of t times y1 prime. That also involves C1. And the last term involving C1 is the one right before the last term. That's plus q of t times y1. Okay, and then I'm going to group the terms with involving C2 and rewrite those out. So we have C2 times y2 double prime plus p of t times y2 prime plus q of t times y2. Okay, so those are the one involving C2. Well, now, what do you notice? What do you notice about this one? What can we replace this with? So, yeah, 0. But before I use 0, I'm going to write one more step. Okay, so that's really L of y1, right? And that is 0, because that's coming from the assumption. And then the second part, which I'm going to highlight, this one, that's L of 2, which is going to be 0, because that's our assumption. So we have plus C2 L of y2. Well, so what have we proven? We have proven that since L of y1 is 0 and L of y2 is also 0, it follows that L of this linear combination of them, C1 y1 plus C2 y2, is also 0. Okay, so we have proven the claim. So you can write one more statement, hence regardless of the constant C1 and C2, L of, well, let's do it this way. So regardless of what the constants are, the linear combination of C1 y1 plus C2 y2 is also a solution. Okay, so there you go. I put a box at the end. Or you could put QED. That also means the proof is completed. So that's the proof you are required to know. Know how to prove the superposition principle. So any questions on this proof? Now, okay, so now let's bring in the idea of the Wronskian. So before I move on to the next theorem, I'm going to show you something. So we claim that this, so what did we claim? We claim that the general solution, so we claim that the general solution is y equals the linear combination of y1 and y2, c1 y1 plus c2 y2. Now the big question is this is this the general solution? Or is there more solutions that we don't know about in a different form? Well, how can we check that? So that's the next thing I want to talk about. How can we check that this is the general solution? So we're claiming that possibly it is the general solution. So how do we address this question? So we want to know if this contains all the solutions. Okay, so that's what we want to know. So that's like the big question. Is this enough? So how do we proceed? Well, if I give you an initial condition, right, and you plug it in accordingly, then you give me a particular solution, right? So let's prove that. If given an initial conditions, so let's call it the initial condition. So say I give you initial condition y evaluated at t naught is y naught, and y prime evaluated at t naught is y naught prime. Okay, so any arbitrary initial condition just at any single point. Okay, so that means, how would I solve for C1 and C2? Well, I plug this into my differential, I plug this into my solution, right? Which I'm claiming it as the general solution right here. So let's do that. So if I plug these initial conditions in, I have y, so C1, y1 evaluated at t naught. So we have C1, y1 evaluated at t naught plus C2, y2 evaluated at t naught is equal to y naught, right? So that's the first initial condition. Now the second initial condition, you plug into the derivative of y. So that would give us C1, y1 prime evaluated at t naught plus C2, y2 prime evaluated at t naught equals to y naught prime. So I know I'm giving you a lot of symbols, but just make sure you understand them, and if something is not clear, let me know so I can explain it again or maybe rewrite it in another way. Okay, so what I'm doing, I'm applying the initial conditions to y, which I'm claiming it to be the general solution, because that's the way you would be solving for C1 and C2, right? Now here's the thing. So from here, we want to talk about, so now think of this as a system of equation. So if you remember, that's what we did yesterday. We kind of derived a system of equation to solve C1 and C2. So do you guys remember that yesterday? Right? Yeah, so Shuman says yes. So that's what we did with one example. We created a system of equation where your unknowns were C1 and C2. So this is what we're doing, where we have a system and we want to solve it. We want to solve for C1 and C2. Now, to solve that, we're going to have to borrow Kramer's rule. So this is where Kramer's rule comes in. Okay, so I don't know how many of you did the small research I wanted you to do, but if you didn't do it, that's fine. If you did it, this will make more sense to you. So those of you who did it, great. So the determinant of the coefficients is, so if you were to take this content and replace everything with simpler version from Kramer's rule, this is how it's going to look like. So before I introduce the determinant, I just want to give you a flashback on algebra. What is this coming from? So think of it this way. Okay, so if you have a system, say AX, let's see, how would they write it in an algebra class? So if I have A1, right, X plus B1, Y equals to C1, and then I have another system, A2X plus B2Y equals to C2. Right? So probably something like this, you have seen it in the past where you are solving for X and Y, right? So you would set up a matrix to solve this, which we call it the determinant, D. So the D is going to be this matrix, which is the coefficient of X and Y. So the first column is coefficient of X, second column is the coefficient for Y. So you would have A1, A2, and B1, B2. So that will be the determinant of the system. Do you recall this? Maybe? Yeah, okay. All right. So how do you compute this matrix? How do you find the determinant? Do you guys remember this? Yeah. So you would do this as follows. A1, B2 minus A2, B1. That will be the determinant of this matrix. Now, that's only the determinant. That doesn't tell you anything about X and Y yet, right? So how would you find X? How would you find value for X? Well, you come up with another matrix, okay? So to find value for X, it's going to be the determinant of the X column over, well, so it's not really determinant of the X column. That's silly to say. But I'm just going to give you a notation and then I'll explain. I don't know the exact word they would call it, over the determinant of the entire system. That's D. Now, what is this D sub X, right? So now that's the next question. Well, D sub X, it's the matrix that you set up. You replace the coefficient of the X values with these coefficients C1 and C2. So this is how it looks like. You have the matrix. So because you're solving for the determinant dx, you replace the first column with C1 and C2, and B1 and B2, they just stay as it is. And that's the matrix for dx. I call it determinant of x, but that's not the right word. And this will just be simply C1 B2 minus C2 B1. So you get a number for dx, you get a number for d. Well, x is going to be dx over d. That's how you find x. Now, what do you think? How would you find y? What do you guys think? Right. Thank you, Suman. So you would replace now the second column, because those are the coefficient of y, with C1 and C2. So I will label that determinant as d sub y. So that would be, so A1, A2 remain unchanged. Second column will be replaced with C1 and C2. And again, you multiply these coefficients in this form. So you have A1, C2 minus C1, A2. So all of these are just numbers, okay? They're not variables, they're just numbers. So that means y can be computed as dy over d. So that will be the formula to compute y. And that's Kramer's rule. So this is the brief review of Kramer's rule for a 2x2 matrix or 2x2 system, okay? Now, we're going to translate all of this into the left side, where everything is now replaced with differential equations, solutions, and constants, okay? But the idea is really coming from Kramer's rule. Now, what are our unknowns? Our unknowns are C1 and C2. So the role that C1 and C2 are playing is X and Y for Kramer's rule, okay? So we're going to set up this matrix with Y1, Y1 prime, Y2, Y2 prime, because those are kind of like your A1, A2, B1, B2 matrix. So we are going to set up this matrix. So we have the following matrix. So the first column is for C1 coefficients. So that's going to be Y1 evaluated at T naught, Y1 prime evaluated at T naught. And the second column will be the coefficients of C2. So I have them in reverse order when I wrote the equation, but these are the coefficients. So we have Y2 evaluated at T naught and Y2 prime evaluated at T naught. Okay, so for simplicity, I'm going to ignore the T naught, okay, because that's just evaluation. So if I were to rewrite this matrix in a simpler form, so I'm going to put 3 equal sign. So you have Y1, Y1 prime, Y2, Y2 prime. So all I did was ignore the T naught notation because it looks huge when you look at it, but it's not really that huge. It's a very simple idea to understand. So now, how do I find this matrix? Well, I follow the rule for matrix multiplication, right? So this would be y1, y2 prime minus y1 prime, y2. So this is the determinant of this system, and this determinant is what we call the Wronskian. So this is what we call the Wronskian. Okay, so this is the Wronskian, and sometimes we would use the notation W of y1 and y2. Wronskian of the two solutions, y1 and y2. So this is something you want to remember. Okay, so the Wronskian is this magical formula. So only if I can make this box. So never mind. So any questions up to here? So this is important. You have to remember what is the definition of a Wronskian. Okay? But what do we really get it from? Well, we get it from the idea of Kramer's rule. Okay? So having said that, well, now the question is, so I introduced what the Wronskian is just the determinant of the coefficient of this matrix after applying the initial conditions, okay? Well, now we still haven't answered the question, right? We still haven't answered, can we find C1 and C2? The answer is yes, right? So we found the Wronskian, which is the determinant of the entire system, but now what if I want to find the determinant of only C1, right? So what do you think I'm going to do? So I want to find the value for C1. So just like here on the left side, I wanted to find value for X. Well, I had to compute this another matrix, which was replacing the first column, because that's where the X was, and with the constant C1 and C2. Now coming back to this one, I want to solve for C1, which is playing the role of X. So that means I'm going to be replacing the first column with y0 and y0 prime. So C1 can be computed by using this matrix. So we have this matrix. So it's going to be the determinant of C1, right? Because that's what I'm going to replace it with, over the determinant of the entire system, which is the Wronskian. So I'm going to rewrite it using our notation. So C1, therefore, is going to be the matrix. So I'm replacing the first column with the point y0 and y0 prime, and second column remain unchanged. So that's y2 prime. So that's the determinant of C1 all over the determinant of the entire system, which is really the Wronskian. So that's how you would compute C1, okay? Just like you compute X. Now, how would you compute C2? Exactly, exactly. Thank you. So this would be, so we keep the first column unchanged. So that's y1 prime. Now, second column, you replace it with y0 and y0 prime. All over the Wronskian, so that's that. So these are the values for C1 and C2. Now, because the Wronskian is in the denominator, what happens if the Wronskian is 0? Alright, so we run into trouble. So this is true as long as the Wronskian is not 0. Okay? So that's the conclusion we're going to draw. So if the Wronskian is not 0, then we have unique solution. So that means now we can solve for C1 and C2. So that's the conclusion we can draw. So we have answered the question that as long as the Wronskian is not 0, then this general solution that we claim is the general solution. There is no solution in any other form. So we have shown that the claim holds. Okay, so that's the final statement. And within the claim, we were able to introduce an idea of the Wronskian. Okay, so, and here is another remark for you. So here is a remark. So if the Wronskian of y1 and y2, so any pair of solution, right, is non-zero, then we say that y1 and y2, they form a fundamental set of solutions. Okay, so that's another remark to know for Wronskian. So when it is non-zero, it gives us a unique solution, so you can solve for C1 and C2 in this form, using this matrix formula, you can say. And also we know that the two solutions, y1 and y2, they form the fundamental set of solution. Fundamental set of solution just means you can get every solution from this set of solution. You don't need any other solution to give it to you. Okay? And more importantly, they're linearly independent. Linearly independent. Okay, so that's the remark on Wronskian. All right, so any questions? Okay, so let's do an example. Let's do the following example. So here's our first example. So compute the Wronskian of y1 and y2. So say y1 is equal to e to the negative 2t, and y2 is equal to, let's do e to the negative 3t, okay? So to compute the Wronskian, well, we apply the definition of the Wronskian. So we know by definition the Wronskian of any two solutions, y1 and y2, is equal to this matrix y1, y1 prime, and y2, y2 prime. Right? So that's the definition of the Wronskian. So I'm going to place in y1 and y2 and take their derivative as well. So we have the matrix of y1, that's e to the negative 2t, and its derivative on the bottom, so that will be negative 2 e to the negative 2t. Okay. Second column is for y2, so we have e to the negative 3t, and right on the bottom you have its derivative, so that's negative 3 e to the negative 3t. So that's the matrix we set up, and now we do the matrix multiplication. So we do negative 3 e to the, so you have e to the negative 3t and e to the negative 2t. We can add them up, right? E to the negative 5t, and then minus, so that's plus 2 e to the minus 5t. And then if you simplify this, this is just negative e to the negative 5t. So that's the Wronskian for these two pair of solutions. Any questions? Okay. Does this make sense, guys? All right. Thank you. So how did I get negative 5t? So I got negative 5t by combining their exponent. So if you do e to the negative 3t times e to the negative 2t, well, from algebra we know same base, you add up their exponents, so it's e to the negative 5t, right? So this is from I don't know, from, let's just call it a recall. Okay, so purely algebra. So again, that's the nice thing about this course. You learn something, and then within it, there's so much algebra, right? It wouldn't be 10t because you're adding the exponent, right? You're not multiplying. When you're multiplying the base, you add up the exponents. That's the laws of exponent. Yeah. All right. So point. So let's do another example. Let's check this one out. So show that y1 of t, which is this function t to the power 1/2, and y2 of t, which is this function t to the negative 1, they form a fundamental set of solutions of the equation 2t squared y double prime plus 3t y prime minus y equals to 0 for t greater than 0. Okay, so how do you show how do you show that the pair forms a fundamental set of solutions? this is when we're going to use the remark, right? We're going to compute their Wronskian. If the Wronskian is non-zero, then we know they form a fundamental set of solutions. Okay, so again, we're going to compute the Wronskian of y1 and y2. Does this make sense? Okay, let me know if you guys have questions. So I'm going to go ahead and compute their Wronskian. All right, so Imrose says yes. Hope most of you are following. All right. So let's compute the Wronskian of y1 and y2. So we set up the matrix y1, y1 prime, y2, y2 prime. So we have y1, which is given to be t to the 1/2, and then you have to compute its derivative. So we compute the derivative of t to the 1/2. That would be 1/2 t to the minus 1/2, right? And then y2 is t to the minus 1. Compute its derivative, negative t to the minus 2. And now we try to find their Wronskian. So we have negative t to the, so 1/2 plus negative 2, so that's negative 3/2, right? Minus 1/2, and then t, so now we're doing negative 1 plus negative half, that's also negative 3/2. And then together, if I combine them, I get negative 3/2, yeah, t to the minus 3/2. And this is not 0, so for t is greater than 0. So what do we say? We say that since the Wronskian is not 0, for all t greater than 0, we can now conclude that y1 and y2, they form a fundamental set of solutions. Okay, so if the Wronskian is not 0, then we have a fundamental set of solutions, which means we can get all the solutions just from y1 and y2. Okay. All right, so any questions on the Wronskian? Okay. Are you guys okay so far? All right. Okay, so the next theorem that I'm going to prove is Theorem 3.2.7. So I did crop that one as well, so it's not here. Okay, so it's here. Okay, so this is the next theorem we're going to prove. So I know this is a lot to digest in one day, but we have to do this, so just be with me. So here's the next theorem we're going to prove. Now this is another major theorem because it has a name, right? It has a name of the person, so it's important that we know the proof. So this one you must know the proof. Okay. All right, so what does it say? So again, if you have two solutions, y1 and y2 of the given differential equation, where p and q are continuous on an open interval I, then the Wronskian is given by this formula, okay? So I'm going to rewrite this. So this is really as c times e to the integral of negative p of t dt. So sometimes the textbook would spell it out as exp to represent the exponential part. So this is another way we can redefine the Wronskian, okay? So we have the definition of the Wronskian, which was this matrix right here. Now Abel's theorem tells us that, hey, if you have a differential equation second order, and if y1 and y2 are two solutions to that differential equation, we can actually compute the Wronskian in this form, which is c is some arbitrary constant times e to the integral of negative p of t dt. Okay, so this is another way you can redefine the Wronskian. Now furthermore, Wronskian is 0 for all t if c is 0, right? Or it's never 0 because it's an exponential. It can never be 0 unless c is 0. So that's another statement to remember. Okay? So we're going to prove this theorem. Are you guys excited? Yeah. Yeah, I know. Just calm yourself, and maybe over the weekend you can go over the detail. But right now just try to understand what is the theorem really saying. Even if you don't follow the proof completely, first time when you see a proof, it doesn't stick. I know that. That's true. For me, it's true. Like, it doesn't stick. Second time, okay, you followed through. Third time, you're getting there. The fourth time, you're probably getting there almost. Fifth time, sure, you got the proof. That's just my analogy. But of course, you can come up with your own ideas of how to really understand a proof, okay? So I'm going to try to break it down as much as I can so that at least you don't have to go to fifth time to understand the proof. Maybe the third or the second time will make sense, okay? So, okay, having said that, so we're going to start with the assumption if statement. So we're assuming y1 and y2 are solutions to the differential equation, right? So we take the if statement and we write it down. So, okay, so proof. So the if statement is assume y1 and y2 are solutions of the differential equation. So the equation has this form. So I'm going to ignore the L of y term. I'm just going to write with y double prime plus some function p of t times y prime plus q of t times y equals to 0. So y1 and y2 are solutions to this. That means when I plug in y1 into this, it equals to 0. It makes sense. When I plug in y2, it also equals to 0. So that's what I'm going to write down next. So that means, so we have y1 double prime plus p of t times y1 prime plus q of t times y1 equals to 0. Because y1 is a solution, right? Now y2 is also a solution, so I can write down another equation. y2 double prime plus p of t times y2 prime plus q of t times y2 equals to 0. So I have two equations, right? So let's call this equation 1. Let's call this equation 2. Okay, well, what do we want to show? We want to show that the Wronskian is this exponential expression. Okay, so let's be clever, okay? So we're going to do the following. I'm going to multiply equation 1 by negative y2. Yeah, right? Yeah, so it's going to work. So we're going to multiply equation 1 by negative y2, and one more thing, we're going to multiply an equation 2 So I'm going to multiply that one by y1. Okay, so these are the following steps I'm going to make. So let's see how it becomes. So we multiply equation 1 by negative y2. So I take this, multiply it by negative y2, and I take this one, multiply it by y1. Okay, so then we have the following equation. We have negative y2 y1 double prime minus p of t times y2 y1 double prime, no, not double prime, sorry, y1 prime plus minus because I'm multiplying by negative y2. So let's write it this way: q of t times y2 y1 equals to 0. Okay, and now the second equation would now become what is that going to become? y1 y2 double prime plus p of t times y1, right? y2 prime, okay? And then the last term would be q of t times y1 and y2 equals to 0. Okay, I hope I didn't make any mistakes, but let me just double check all the terms. Okay. Yeah. Okay, that looks good. Well, now we have a system of equation, right? So I'm going to add them up. Okay. When I add them up, what happens? Something really nice happens. So if you notice, these are like term, right? And they differ by a sign, so they go to 0. Yeah, that's really nice. Okay, so what happens? We have the following. We have, so after I add them, I get y1 y2 double prime minus y2 y1 double prime plus p of t times y1 y2 prime minus y2 y1 prime equals to 0, right? Because the third term, they disappear, they go to 0. Well, now something really clever happens. What do you notice? So someone tell me if they notice anything. If you don't notice anything, that's also okay. So, all right. So, if you notice, so Aisha, so what I'm seeing is that you should see the Wronskian popping up in this equation. Do you see that? The definition of the Wronskian. So if you look up your notes, right? So you should see that this is the Wronskian. Okay? And that's the Wronskian, and here are the second derivative terms. So this is the Wronskian prime. Okay? That's the nice thing that happens. This is really cool. So now what do we have? We have the following. We have w prime. I'm going to call it w because it's the Wronskian. Okay? W prime plus some function p of t times the Wronskian equals to 0. Now, how do we solve this equation? Yeah, it's linear and what else? So if I were to write w prime as dw dt, you will see that it's also separable, right? So Suman, yes, you're correct. But I'm going to leave there because somehow I want the exponential to appear in our conclusion, right? So we're going to use the linear method. But this is also separable. So you can use either of those. But we're going to go ahead and use, actually, you know, I changed my mind. Yeah, it doesn't matter which way you do it, but I'm going to go ahead with separation of variable. I think that's going to be the easier way to do this. Do you guys have any questions? So Aisha, yes, this is separable. So let's do separation of variables. So I'm going to rewrite w prime as dw dt, because separation of variables is always nice and neat. And then we start separating the variables. So we have, where we get? We get dw over w is equal to negative p of t dt. You would have gotten the same result if you use integrating factor. I think you see it right away when you do that, probably. Yeah. Or now I'm going to go ahead and integrate both sides. So my integration symbol looks really weird. Okay, now it's better. So we have the integral of 1 over w, that's ln of w. And, well, on the right side, you can't really integrate, right? It really depends on what the function p of t is. So we're going to leave it as the negative p of t dt. So it just remains like that. Well, now the next step is to solve for w. How would I do that? Right, so we have, yep, absolutely, dt. And I'm also going to bring in my integration constant plus c, because I integrated the left side, but I didn't integrate the right side. So let's still keep plus c in there. So now if we exponentiate both sides to find w, w is equal to e to the integral of negative p of t dt plus c, and then that plus c can come out as the integration constant. So hence w is equal to c times the integral of, no, sorry, c times e to the integral of negative p of t dt. And that's what we wanted, right? If you look at the statement, isn't that what we wanted? We wanted to show that the Wronskian is equal to that expression, c times e to the integral of negative p of t dt. So there we have it. We have completed the proof. So that's pretty nice and neat. Now let's make the final statement. So note that since the Wronskian is an exponential, expression, either it is never zero, right? Because exponentials can never be zero, never zero. So that means c is not equal to 0, right? Or it is always 0 if c is equal to 0. So that completes the proof. So there we have another proof for section 3.2. So this was a very theoretically heavy section, okay? But we got through all of them, so that's a success. And the final proof was this one, Abel's theorem. Very important theorem, very useful theorem as well. So make sure you understand the statement. Try to digest the proof as much as you can. Make sure every step makes sense. If you want to rewrite using your own notation or notation that you like, just make sure you rename them. So yeah, there we have it. So any questions on this? So so if there are no questions, let's do an example and see how to use Abel's theorem. Okay, so let's do a little bit of computation. So if you want to take a break for like good 10 seconds, just relax your hands and then come back to it. Do that. So I'm going to go ahead and start writing an example. So no, actually I want to do a different example. So let's do this one. Let's so given y double prime minus 4y prime plus 3y equals to 0. Use Abel's theorem to compute the Wronskian. Okay, so you don't necessarily have to be given the solutions, y1 and y2. You can always compute the Wronskian if you know the differential equation, because from there you can pick up what is your p of t and then just plug it into this formula that we just derived. Okay, so we know from Abel's theorem that, we know that the Wronskian is equal to c times e to the integral of negative p of t dt. So you don't really have to know the solutions, y1 and y2. So what is p of t in this problem? Right, so p of t in this case is negative 4. So we're going to plug that in and see what is the Wronskian. So the Wronskian is going to be some arbitrary constant c times e to the integral of negative 4 dt. So that would be c times e to the positive 4t. So there we go. We have the Wronskian. Even if we don't know the solution, we can still compute the Wronskian by picking up what is the function p of t is. Okay? So any questions on this? All right. So yeah. So that's the end of 3.2. Any questions? Now, I would like to do another example before I move on to 3.3. Let me know if you guys have any questions. All right, so thank you, Aisha. So before I move on to 3.3, I want to just work through another example of Wronskian, just show you how the question could also be worded and could be useful. So here's a question from the textbook. This is from section 3.2, so we're still on that. So find, well, actually, I'm going to do a different one. So let's try this one. So if the Wronskian of f and g is 3 e to the 4t, and if f of t is equal to e to the 2t, find g of t. So here's another problem where the concept of Wronskian is used, and it's useful. So the Wronskian of any pair of solution, by definition, is this matrix y1, y2. Oh no, sorry. I think my brain just moved everything around and it misplaced my matrix entries. So this is y1 prime, y2, y2 prime. That's the correct entries. Okay. All right, so that's the Wronskian we know by definition for any two pair of solutions. Now for this problem, we're given the Wronskian, which is 3e to the 4t, and you're given one of the function. So you're given f, which is 2t, and you're looking for the second one. How do you think we're going to approach this problem? So I'll give you a few seconds to think about this. Yep, absolutely. So we're just going to plug these in. So instead of y1 and y2, the book is using f and g for this problem. So I'm going to replace y1 and y2 with f and g. So we have the Wronskian of f and g. It's going to be the matrix f, f prime, g, and g prime. Okay, so just renaming them. We know the Wronskian. That's 3 e to the 4t. And on the right side, we set up this matrix. We know one of the function f, which is e to the 2t. We know its derivative, right? Thank God to calculus. We know how to differentiate. And then g is the unknown function. So g and g prime. So that will be the setup. And now we try to figure out what is this function g. So let's go ahead and compute this matrix. So we have e to the 2t g prime minus 2 e to the 2t g, and on the left side we have 3 e to the 4t. That's the setup. Now I can reduce this a little bit more to perform my work, so I'm going to go ahead and divide everything by e to the 2t to simplify. So we would have 3e to the 2t is equal to g prime minus 2 g, right? Yeah, okay, it looks good. Now, how do you solve this? This is a first order. This is first order. Which method can you use to solve this first order? So this is going back to chapter 2 now. What do you guys think? Yeah, it's linear, right? So all I have to do is kind of rearrange them so it looks familiar to our eyes. So it's first order linear. So I'm just going to rearrange. So we have g prime minus 2g is equal to 3e to the 2t, right? We're used to seeing it this way, where the function is on the left side and just some arbitrary function is on the right side. So we have g prime and g on the left side. So we look for integrating factor, mu. So I'm hoping you guys remember this, right? This is from before. So what is this mu of t? That's e to the integral of p of t, that's negative 2 dt. That's e to the negative 2t. So that means our differential equation now becomes mu, which is e to the negative 2t times g, its derivative. And on the right side, we have 3. Because e to the 2t times e to the negative 2t, they cancel out, right? And now we go ahead and integrate both sides respect to t. So the left side is e to the negative 2t times g. On the right side is 3t plus a constant c. And the last step is to solve for g. So therefore, g is this magical function 3t e to the 2t plus c e to the 2t. So there you go. Another algebraic questions using the Wronskian. So this was a nice question. So you were able to use the idea of the Wronskian and some algebraic work, and then it reduces to somehow first order linear equation. So you have to recall how do you solve this using integrating factor, and from there we were able to compute this function g. Any questions on this? Aisha, sure, you can ask questions. 2t divide. Oh, divide 2t. Let's check. Um, I'm not sure which step you're on. So up to here, are we okay? Mu is equal to e to the negative 2t. So the last one, okay. So the last step, right. So I divided by e to the negative 2t. So here, I didn't show steps. So g is equal to 3t over e to the negative 2t plus c over e to the negative 2t. Well, again, from laws of exponents, if the exponent is negative on the bottom, you can bring it on top. It makes it positive. So that's 3t e to the 2t. And then the same thing for the second term, c e to the 2t. So this is laws of exponents. So I didn't show the steps because I thought this was understood from laws of exponents, okay? Right, so yeah, you're absolutely right, Aisha. That's how you would do it, but I just I just mentally put it up there because I thought it was understood. But thank you. Okay. All right. So any questions on 3.2? 3.2 is a heavy section, so I do know that, and I'm aware of that too. So just make sure you follow these notes and follow the steps. And if you need more detailed, you can look at the textbook. The textbook does the same proof, but maybe in a different wording. So, but the steps are all the same. So you can look it up, use another resource to help you better understand if you need more resource. But I think I went on a lot of details to prove these theorems, so it should make sense. If not, then let me know. Okay. All right. So sorry, come back again. So this is the last question. All right. Okay, so that's the end of 3.2. So I'm going to go ahead and start with 3.3. So starting with section 3.3. So 3.3, we're going to study complex roots for second order. So 3.3 is for complex roots of the characteristic polynomial. So I talked about this very briefly yesterday, that when we have the characteristic polynomial, because it's second degree, either you can have real distinct root, which we saw yesterday, you can have complex root, meaning when you're using the quadratic formula, you have a negative value inside the radicand, right? Or you can have, if the radicand is 0, then you have repeated roots. Those are real. So this is the second case where we have complex roots for the characteristic polynomial. So starting with, so continuing with the second order linear differential equations. So we looked at the form a times y double prime plus b times y prime plus c y equals to 0, right? Where our coefficients are all constants, so a, b, c are all real numbers, okay? So in 3.1, we assumed our solution form is y equals e to the rt, right? Where r is a real number. So that was in 3.1. Now in 3.3, we are going to discover that there are not only real distinct root, you can also have complex root, right? So suppose we have the following characteristic. So suppose we have the characteristic polynomial to be a r squared plus br plus c equals to 0. That's a quadratic equation, right? If you were to think of it in algebraic form or in algebraic vocabulary, it's a quadratic equation. Well, let's say I want to solve for r, right? So we can recall r is equal to negative b plus and minus square root of b squared minus 4ac all over 2a, right? The famous quadratic. So never forget the quadratic. Always remember that quadratic formula is your best friend every time you have a quadratic equation. Even if you're not so great with factoring, always come back to the quadratic formula. Now, what are the different cases we can have with this for r? So because it's a second degree, we're expecting two solutions, right? Two values for r. So we call them r1 and r2. So here are the different scenarios you can have, where everything really depends on this piece right here. Well, that's what we call the discriminant, right? So that's the mathematical term for that term, the discriminant, b squared minus 4ac. So here are the different cases. So if b squared minus 4ac is positive, we have real distinct root, right? So if b squared minus 4ac is greater than 0, meaning positive, we have two different values for r, so r1 is not equal to r2, right? So we have real distinct root. So that's what we saw earlier yesterday. Now what if, second case, if b squared minus 4ac is less than 0? What kind of values for r are we looking at now? Imaginary, right? Which we call them complex. So we know r1 and r2 are complex, they're so let me call them complex conjugate. So you might have seen the imaginary I test. So screen is off. Can you see my screen? I think I'm still sharing. Okay. All right. Okay. All right. So I don't know what happened, but I think I'm still sharing. It doesn't give me any notification. So this is where we are at. We have b squared minus 4ac is less than 0, meaning negative. So we're looking at complex roots. The third case, which I'm going to write down, that means when b squared minus 4ac is 0, that means you're only looking at one value of r, right? So b squared minus 4ac is 0, so you only have negative b over 2a. There is no plus and minus to give you other roots. So the third case, that's going to be 3.4, I believe, is if b squared minus 4ac is exactly 0. Then we have r1 is exactly equal to r2. So this will be real repeated roots. So this is going to be section 3.4, I believe. So I'm just going to put a question mark because I haven't verified that yet. Okay, so we're on the second case where our discriminant is going to be less than 0. So we're looking at complex conjugate. Now, before I start looking at the solution, I do want to give you a brief intro to what are the complex numbers. Okay, so just in case you haven't seen it yet, this would be the time you want to review complex numbers. Just a little bit, not a lot, because I will give you the review with me. So what are complex numbers, right? So complex numbers so they're numbers in the form of alpha plus or minus beta I, right? So this I is what makes the real number imaginary, right? So where alpha and beta, they're real numbers, where I is the one that makes it imaginary. So I is imaginary. Have you guys seen this anywhere in the past? Yeah, right? You probably have seen it or not, but Saisha didn't, Alex did, Mosa did. Okay, good. So some of you have, some of you haven't. So we don't really study complex number a lot, but you see them once in a while. So maybe that once in a while haven't come yet. So here's the time where you see them, maybe for the first time, maybe not. I has a special value. Okay, so this is a sort of like a review so we can write out solutions in complex form. Okay, so we're going to get there, but let's do a little bit of recap. What is the value for I? So Alex and Musa, you said you've seen it. Do you guys remember what is the value for I? So yes, so Bethany says yes. Square root of -1. Thank you. So this is a square root of -1. That's the value for I. Now I'm just going to write down few powers of I so that when I give you another magical formula, it will make sense. Okay. Now what happened if I write down I square? What is that value? If I square the square root of negative, yep, -1. Thank you. Now what if I do I cube? What do we get? So if I square is -1, if I multiply that with I, So that gives me I cubed, right? That would be what? So it will be negative I. So M rows and yes, negative I. So I'm going to write down just a few more. What about I to the fourth? So I to the fourth, it's going to give us 1. I to the fifth. So what is I to the fifth? I, right? So, and then what about I to the sixth? Last one. So this would be negative 1. Okay. Hopefully you guys can see the pattern, and yeah, it's a loop, right? It just keep repeating that same pattern as you raise I to odd and even power. Okay. So okay, we're not gonna need all of this, but I up to I to the sixth is good enough, and then just keep going, right? No, why am I doing all of this? Well, I have a reason why I'm doing all of this, right? I want to derive a formula for you, okay? So I want to derive Euler's formula. So that's going to be coming up. We're going to be using Euler's formula to write out the solution to the differential equation. So this is coming up tomorrow. Okay, so before I do that, I do want to mention, do another research, okay? Research, what is e to the x? The summation for this. Okay, so uh, so if you have time, power series for e to the x, and then sine of x and cosine of x. So see if you can do those two research for tomorrow, before tomorrow, so that way when I'm talking about series stuff, it'll probably make sense a little bit more. Okay, so that's where we're headed next. I'll finish up 3.2 tomorrow, give you the guidance to what to expect for the first test, and then we'll see how far we go tomorrow. So wherever we stop, that's where I'll draw the line for exam 1 tomorrow. Okay.